Let's pop out the chats. Look, see if everything works. Yesterday we had some issues with the stream setup, but I think today it works reasonably good. Okay. So, let's open this. Hello everyone and welcome back to yet another live stream. Yesterday we were, we're still in the process of building an example HTTP server in Odin to get a feeling for the language. Yesterday we started porting the macOS implementation with KQ, and we started porting it to Linux, to Linux's epoll, which is somewhat similar to what macOS has with their KQ, basically an event polling mechanism where we submit a couple of file descriptors we are interested in listening to, and then when something becomes ready, we get a notification. Someone on the stream yesterday mentioned that we can also directly use IOUring, which is a fundamentally different API. And we will discuss that today as well. But today we want to look at IOUring and maybe get the first implementation done, the migration from epoll to IOUring. And I want it such that we can have both implementations side to side and see how they compare with each other. I think that's fair enough. So let's get started. Okay, so let's actually open this here. Open Excalibur. Today, magically, the drawing board magically got to work again. So, we have epoll. Epoll and KQ. And on the other side we have IOUring. Oh man, somehow this thing doesn't work so good here. It doesn't track it very well. I don't know if that's the driver or whatever, but on macOS it's a lot better. Okay, but whatever. So these two are essentially the same, epoll and KQ. And what it boils down to is we have some list of file descriptors, fd0, fd1, fd2, fd3, and these are the file descriptors we're interested in. And maybe this is the server socket, and these three other file descriptors are for client sockets. And what we do is, okay, we say we are interested in this and add them to the list of the interest list. And then what we do is we call epoll wait or KQK event, and this function essentially waits for as long as any of these file descriptors do not get any data. But when some of these file descriptors get data, we epoll wait returns and returns us the number of events that it detected. And then we can handle these events one by one so that everything works well and we don't have to constantly spin and see whether data is available or not. Now, IOU ring. So this is more like a polling mechanism. Or event-based. Whereas the other, IOU ring, is fundamentally different. So here we have true asynchrony in so epoll allows us to have multiple file descriptors managed in a single thread and poll on them whenever one is ready. But this is not true asynchrony because we still use one thread to poll all of these. So we cannot overlap work with reading from the file descriptor. IOU ring allows us to do that. So it allows us to overlap work on a user space thread. Hi, insmod32. It allows us to overlap work on a user space thread. So we have what the heck? So now my mouse disappeared. And so we have user space and we have kernel. And these are obviously separate. What IOU ring now allows us is to overlap work in user space with work in the kernel, that is reading and writing from file descriptors, which is not possible with epoll. And you do that by introducing two communication channels. And these two communication channels are called a submission queue and a completion queue. I did it with a virtual file in sys, okay? Completion queue. You can also do this somehow manually by having two threads where one reads and the other one sort of does not, but this allows for having the kernel do the read, and that obviously has the advantage that we don't have that many task switches and it should be more performant. So IOU ring will spin up a new kernel thread that polls on this submission queue. Then we submit entries into this submission queue. And once the kernel thread is done with one entry, it returns that entry back onto completion queue and we can do work with it. So the idea I have is whenever we accept a new connection, we add a new read call to our submission queue. So first is accept, then we add a read call to our submission queue. The next thing, I mean, we sort of question mark here, because should we do that every time? Can't you send a signal from the kernel to the process? I'm not sure what you mean by that. yeah. So we add a read to the submission queue. Then we do nothing. The kernel reads at some point when data is available and adds it to the completion queue. So when something is completed, you send a custom signal to the process, then you don't need to wait. When something is completed, you send a custom signal to the process, then you don't need to wait. Yeah, I mean, IO Uring works by looking at the submission queue and the completion queue. So basically what we would do is add all these things to the submission queue and then maybe on a different thread, but I don't know. I read the completion queue, and once the completion queue has some entry in it, we, the kernel adds to the completion queue. And once that's done, we obviously poll the poll completion queue. And when we got something, we handle the connection. IO Uring is awesome. Yeah, I only did something with it once, and we will see how it goes. But could I ask what gave you the idea? I knew that it existed, and I kind of wanted to explore. I kind of wanted to explore how is it possible ways to integrate it into our HTTP server and see how it performs against epoll and KQ. But also what I saw is that there is already an HTTP server implementation in Odin, and they did something with IO Uring, I suppose. Actually, I'm not sure. I thought it had something. Yeah, here, IO Uring. I don't know how they do it, but they have something. Thank you for the follow. Yeah. I don't know, so we'll see how it goes. Maybe we need 2 threads for this. One thread that basically accepts and adds to the read. I'd hope that my implementation might have piqued your interest. You have done it with IO Uring as well? I haven't saw that. Yeah, okay. Nice. Okay. Yeah, and that's also the reason why we are on Linux now. What does your HTTP server serve? At the moment, it just serves static assets. I have a folder that's called assets. And feel free to take a look for a quick reference on one way of using Uring. Yeah, I will do that. We basically serve an index.html file and an about.html file. I think it should broadly fit into your existing structure. I don't think they wrap Uring though. I think we have to write the bindings ourselves. I think they don't. Oh no, they have it. Okay, that's good. But the actual IO request mapping might prove a bit funny. Yeah, I don't know. We will see how it goes. Something else I wanted to do is fix this compiler thing so that I can have a quick fix list in for my NeoVim, but I don't. Uring only gives you a void star or UN64. Yeah. So you need to point to some state. Yes, that's what I'm doing right now as well. I have the index into my connection list as a state to the connection, as a reference to the connection. For multi-traffic servers, it gets a bit funky. Yeah, I think that, yeah, I suppose that's true. That's always a little bit of an undertaking. Okay, so let's open this up. At the moment, we have a main for Linux and we have a main for, anyway, I have to head back to work. Yeah, have a nice day. We'll try to catch the stream where I can, yeah. No worries. And then we have the server main loop. I think I will pull this out and have a version that uses Uring and one version that uses epoll. Why do I have this? Yeah, okay, I don't know. So if you want to benchmark your server against any others, I would love to see how mine stacks up. Yeah, that would be maybe something that we do in the future. I need to head back to work too. Yeah. Bye. Okay, so I want a server loop epoll, proc, and server loop IO Uring. Hello, bro. Good morning. Good. Yeah, it's not really morning, right? 12 p.m. Or did you get up just recently? Okay, so what I need is probably the connection pool. Connection pool, and also the assets asset store. Just had a surprise meeting at the company and they fired my manager. Oh yeah, that's bad. Okay, same thing here, con pool, connection pool, assets, or asset store, And what we do is also the server socket could be initialized here. So socket, server socket, and this is a net.tcp socket. Okay. And I think, do we need something else? I don't know. So let's just pull this entire thing out. Okay, so I think it's this. Do we even need client and add our client source? Okay. Okay, and then we call server loop epoll. Or more like server loop is equal to odin lang overview. Okay. Server loop when. Let's look at the when statements again. When statements. Odin version, Odin OS. Command line defines. Config foo file. Okay, so I don't know if we can do this. So server loop epoll. Does that work? C open. Conpool 0. Okay, that's something we don't need. Conpool 0. Error. Let's just do that. Error. Let's call it accept error. Undeclared name socket. This is now the server socket. Undeclared name error. Where is it? It's in 50. Unable to accept on socket. What? Error while accepting. That was actually a bug, so unable to accept on socket. Has to go out. GP. Okay, next. Can take the pointer, pool acquire, that's already a pointer. And pool release, that's 79. That's already a pointer. 94 and 98. Client con asset store and 167. Okay, so this would be server loop. Server loop, and this gets the socket, it gets the connection pool 0, and it gets the asset store. Okay, undeclared name con pools. Okay, 109 pool release. Okay, that builds. So what we can do now is say, okay, when, let's do something like use IO uring or IO uring. This is config IO uring, and it's equal to false by default, or maybe equal to true, or yeah, for now maybe equal to false. And we say this is when IO uring, else a server loop IO uring server loop epoll. Yeah, that doesn't work. So what we have to do is probably IO uring else. So server loop is equal to server loop IO uring server loop epoll. Okay. That's good. Let's see if this still works. HTTP, that's netcat localhost 8080. Let's also open this up. Oh, I don't want to print this. Okay, that's good. So that seems to work. Also in our connection, when odin debug. I don't want this now. Let's just comment this out. And also this. Oh. Okay. Works. Great. Let's also get rid of this. Writer. Let's using. I want to get rid of all these usings as well. It's kind of not very nice. So why did I put this into connection? I thought it was in HTTP. Yeah, it should be in HTTP. Cons per thread. Redeclaration. Good. Okay. So now the IO U-ring stuff. Let's look at the man page. I don't know if I do have this. Oh yeah, we have it. Okay, that's good. So in HTTP Linux, we have to create all of the setup code. Also, there can be a lot of things that can go wrong because we have multiple threads polling on these. So we have to look at we have to look at the memory barriers and where we have to insert some, and also if Odin has memory barriers. Like let's see, fence. As fence, intrinsics. So we have atomic operations. Atomic thread fence. So we obviously have to do this because CPUs are free to reorder the execution of their instructions. And also the compiler can do that. So let's see. So when we read, yeah, we'll see. So I think there was an example here. So let's see, packages, IO U-ring, sys IO U-ring, register setup. So there's something here, but okay, this is just for the sys call. This is the number, I guess. So sys IO uring setup. Okay. Okay, that's great. So we have to write the bindings. And I don't know how we do that. So let's make a T and come back to this. Okay, so Intel Intrinsics Guide. MMS fans. For serializing operation, all stored in memory instructions that were issued prior to this instruction is globally visible before any store instruction which follows the fence in program order. Okay. So what we need to do is something similar to this, but we also have to set up all the code, all the bindings, I guess. So I don't know how we do that in Odin. Maybe we look at this here, plus build Linux. Maybe we need that as well. So there's OS, and there's sys. So sys apparently has all of these structs. Let's look at build docs. Build. Where is it? Overview. Must be enabled with plus build. This is something that's not really well documented, right? So yeah, maybe we just do it like he does. So we make a new folder, Arlo uring, and then we write the bindings. So this, how do we call this? So I suppose they have the foreign functions in here. Yeah, syscall. We need setup and enter. I think that, no, we don't need enter. I think we only need setup. Because, how was it? So if you use enter, it introduces a new syscall, but it prevents the thread from spinning. So we'd have to read through this again. Yeah, so I suppose we don't really have to do the bindings, right? So this is kind of the sys layer, and they call it OS. OS. Check entries. Why did they call it OS? Uring. I mean, it could be in the same file. Okay, this would be plus build Linux. Is that correct? And package IO uring. And then in here, build Linux package IO uring. Okay, first we want to look at sys. And how do you make a sys call? Intrinsics, so it's import base intrinsics. And then we would say something like int uring params. Oh yeah, this has to be contextless. Oh yeah, so it's sys IO uring setup. This is basically the only thing we need. This returns an int. Let's make it a result int. So result is equal to intrinsics.syscall, and I think the syscall Linux, so import core sys Linux, it's sys IO uring setup. Okay. So sys linux.sys IO uring setup. I don't know what register was for. register IOUring register. Oh yeah, maybe we need that as well. So let's just sys IO URing. And how do you do that with contextless? Proc contextless. Okay. This is register. And then we also have enter. So these are the three functions we have to wrap. Let's see, so syscall args. So this is a var args function. So we have to cast this to an int. Okay. Or maybe, I mean, UN pointer is, why is it UN pointer? Interesting. So the setup, syscall Linux. How did that work again? Syscall. Syscall. It was also var args. Okay, good. So let's look at setup. Man IOUring setup. Man IOUring setup. So it takes entries and IOUring params star. So we need something like a struct IOUring params. Oh no, that's IOUring params. Like this. How'd they call it? Okay, that's weird. But does that have a meaning? C struct. Okay, slices. Structs. Packed and raw union. Okay. So like this, IOUring params. Is that about right? And it needs the number of entries. I think there has to be a power of 2 with the least entries. yeah, it rounds it to the next power of 2. So let's just say okay, so uring setup takes entry count u32 and params, which is io, a pointer to io uring params. And then we call it with uint pointer entry count and uint pointer params. Okay, this is the whoop. Why is this? Okay. So register takes a file descriptor. So this would be fd linux.fd, an opcode, unsigned int, so opcode u32 or uint more, uint, I don't know, u32 and io uring setup. Uint, whatever. Void star arc. Okay, how do we do void star? Why is it a void star? Where is arc? Arc points to struct iovec array of nr arc entries. Struct iovec. Is that something that is available in Odin? iovec. Linux iovec. Yeah, okay, so this would be arcs iovec and then uint pointer raw data arcs and uint pointer length of arcs. Right. Opcode. So arcs raw pointer and arc count u32. IO ring register. Okay, so this would be the arc count and this would be arcs. Is that about right? Okay, good. So We only need enter at this point, right? This gets a file descriptor. So let's maybe also make the file descriptor U32. Event pointer fd. I bet you that we messed something up here. Man, IO ring setup. IO ring register. File descriptor, opcode, args, and arc count. Okay. So this gets a file descriptor, U32. It gets a to submit, U32. It gets a min complete, U32. It gets a flags, which may be something else. And a sig set. A sig set. They define sig set? Yeah, they do. Sig set T. Sig, which is sig set. What is a sig set? Okay. It's not too helpful. Sig set T. U32. It's just a pointer to U32. And the size is the number of I don't know if that's true, but we'll see. A size T. See how he did it? Sig set T. And sig over 8 if sig. And sig. We probably never need this. Okay, sig. Sig set. It's kind of annoying that you can't just include these things. Okay, so this event pointer file descriptor uint pointer to submit, uint pointer min complete, and uint pointer flags, and uint pointer sake, and uint pointer size. Maybe also this is just a raw pointer. No, it's a many pointer to a 6 set, right? Let's see if this even builds. Make file. Let's also add io uring sys.odin io uring.odin or io ring. Okay. Now we have to define all of these structs, right? So man io uring params register. Now it's man io uring. I don't know if we have to look at user include Linux io uring.h. Okay, here are the definitions. What if we just I don't know if we should just take all this io uring sqe. So that's something we need. That is something we need. So that's io uring sqe. io uring CQE. What I also wanted to look at was, okay, they had some things here. io ring register, io ring register. Just an enum. Okay. And then io uring params, probably also defined here, yes. So these flags may be something we want to put in there as well. No, io uring CQE. So that's yank. Obviously this won't work. GUIW uring CQE. And io uring params. io uring params struct io. Okay. So this is all U32, so I don't know. Let's just delete this. U32. record a macro, attention, record a macro, go to the beginning, find semicolon, insert U32, escape, okay, this is wrong. U32. No, 3. So these things we don't have. IO SQ ring offsets. So this would be SQ off. We need to include those. CQ off. Also replace the semicolon with a comma. Here as well. Okay, so what we also need is IO uring SQ off. Yeah, IO SQ ring offsets. I mean, basically we have to port this entire header, right? So this is struct. Very manual. Record a macro, go to beginning, find the semicolon, U32, escape this, down. Q. So this is also not right, because now $a comma, no. So this is a U64. Very boring stuff here. And this is, oh. SQ ring offsets, then we also need the CQ ring offsets. Can we make this better? I don't know. This is a U64. 23 up. Remove this. Okay, these things we also have to somehow include. Okay, then this here. This is a gigantic thing. Also U8. Oh my goodness. S32, so this is a U16, this is an I32. This is now a union. How do you do that again? underscore struct. Underscore struct raw union. Is that correct? And then u64 u64 underscore struct. How does that work? An anonymous struct in there? I've never seen anonymous structs. Okay. It's also struct raw union. u32. Oh my goodness, please. u64 kernel rwft, whatever that is. Kernel let's see, kernel rwft, kernel rwft. Is it maybe in here? Kernel rwf, no. What is this? A cint? Cint? Is that even something that exists here? Where's the Odin overview? Ent. Cint. And okay, whatever. We just call it int. I'll make it to do here. To do. This is a rwft, which is supposed to be an int. u32 oh, okay, macro time. This is struct raw union. I don't know why it indents it this all the time. This is a ginormous struct. Oh, this is also packed. So how do you do packed structs again? I don't know if you can do both. So packed. away. Attribute packed. Personality. Struct raw. This was also U16. What the heck? If this is correct, I have no idea. So raw union, raw union. What was that again? U64 as well. How can this be a U80? I don't even understand what that is about. Okay. Don't believe that this works. So this thing is just gigantic. Do we have the params? IO U-ring per. Oh no, we wanted IO U-ring params. We should have that somewhere. IO U-ring params. Okay. Let's see whether that actually matches what's here. So using IOVAX. What does that mean? Using offset. Using So for me, okay, this is offsets. Offset into file. SQ, S-ring, SQ, ring, offsets. Attribute packed. This was just commented out. Command. But they gave it they gave names to it. Also this pack thing, buff index. Okay, that. We have to do using here. Using. Yeah, okay. I don't know. Let's see. Buff group. So they have this kernel. Where was it? Kernel. So this is RF RW flags I32. RW flags I32. Okay. Maybe that's it. Okay, so let's go. Where HTTP Linux. Let's make a good interface for this. So IO ring. Probably a setup proc. Where I don't know what we want to do. We probably need a lot of the flags. These things here. IO ring setup flags. Maybe let's pull them in. Sys IO ring. How do you do bit sets again? Bit sets. Bit set. Bit field is not equivalent to bit set. So bit field, yeah, okay, no. I want bit set. Where is it? Bit set. 0 through this. Okay, we need an enum. How do they do that again? Right, with the epoll creates. Wait. And it was epoll control, right? Epoll control. Epoll control opcode. Bit set. Okay, IO uring setup bits enum u32. These things. leave it like this. QQ, F this, go here, F here, go down, Q, Q, great. So this is 1 shifted over by 0, 1 shifted over, blah, blah, blah. We probably don't need the parentheses. So let's say S, this, replace with nothing, and same thing, this replace with nothing. Good. How does a bit set bits are often used to denote flags. It's much cleaner than defining integer constants. I have to look at the source maybe again. How does it work? Where do they use a bit set again? I used that. I'm pretty sure I did. Like dot add, no. Dot epoll event. Epoll event. There's a bit set of epoll event kind. Epoll event kind. So let's look at envim user include Linux epoll. Where's epoll again? Sys include sys epoll. Epoll events 1, 2, 3. Okay. Out. So epoll in is 1, epoll out is 4. How does a bit set work? 0x 1, 2, 4. Okay, so I guess it's more like so this does the shifting probably for us. So it's, yeah, this probably does the shifting for us. 0, 1, 2, 3, 4, 5, 6, 7. And then IO uring setup flags. Bit set IO uring setup bits, and with some backing type U32. Okay. So setup, I don't know what setup gets, but this calls IO uring setup with an entry count and the number and params. So we need params, io, uring, params is this. We pass in the params and the number of entries, I don't know, 512. Whatever, maybe 128 or 64. Entry count 64. Right? Maybe something like this. Okay, so this will return some kind of file descriptor, but let's just go here, and say setup. Let's just see if this works. Let's just set this here to true and make unclared name setup. So import io uring io ring setup io ring dot setup. Path does not exist. Path does not exist. I thought you can do that. IO uring. So this misses a package thing because it has to be here. Okay, so now we're getting somewhere. Oh, we forgot to do this. U64, I32, U32, and what does that mean? If the ring is initialized with IO ring setup CQE32, then this field contains 16 bytes of padding, doubling the size of the CQE. How did they do it? IO rings. Oh no. No. IO uring SQE. Just commented it out. Big CQE. Expected. Okay, so now it would be nice if my NeoVim would work, right? So maybe that's something we should look at now. But first of all, I have to go and P. Yeah. Okay, so okay, so make 128 expected. This is struct 138 contextless. Where is this contextless? Proc contextless. Oh, okay, this is like this. DA quote, go find this, and contextless. Syntax error, context, oh. Again, DA quotes, go here, go back to the opening quote, contextless. Undeclared name, IO Uring setup. Undeclared name, IO ring. So IO ring. I thought oh, it's sys. IO ring. Okay, this is sys.odin 28. Capitalize this. Make this. We're almost there. Too many arguments. This is 146. Syscall. Still wrong. There's still something wrong. 153. Oh man. What did I do here? Okay, so maybe do it like this. Record a macro F this. W I this. So this is now in HTTP Linux. IOU ring, IO ring, IOU ring. Good. So this builds now. The question is whether it also works. I doubt that it works. But whatever, we're going to see whether it does or not. So, in IO ring and params, we have to set the params here. So look at the man page again. Man IO uring. Let's read through this now that we have the bindings. So IO uring is a Linux-specific API for asynchronous IO. It allows the user to submit one or more IO requests, which are processed asynchronously without blocking the calling process. Yes. Okay, blah, 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 blah. IO ring gets its name from ring buffers, which are shared between user space and kernel space. So we probably have to do some M-maps. This arrangement allows for efficient I/O while avoiding the overhead of copying buffers between them where possible. This interface makes IO uring different from other Unix I/O APIs, wherein rather than just communicating between kernel and user space with syscalls, ring buffers are used as the main mode of communication. This arrangement has various performance benefits, which are discussed in a separate section. Blah, blah, blah. Okay. Setup shared. The general programming model you need to follow for IO uring is outlined below. Setup shared buffers with IO uring, setup, and mmap. Yes. Mapping into user space shared buffers for the submission queue and the completion queue. You place IO requests you want to make on the S queue, while the kernel places results of those operations on the C queue. Good. For every IO request you need to make, like to read a file, write a file, accept a socket connection, etc., you create a submission queue entry or SQE, describe the IO operation you need to get done, and add it to the tail of the submission queue. Oh, this is also, should we put the accept things also on this queue? Maybe. Yeah, we should, right? We should do it. Okay. Each IO operation is, in essence, the equivalent of a system call you'd have to make otherwise if you were not using IO uring. You can add more than one SQE to the queue depending on the number of operations you want to request. That's good. For each SQE you submit, once it is done processing the request, the kernel places a completion queue entry event or CQE at the tail of the completion queue or CQ. The kernel places exactly one matching CQE in the CQ for every SQE you submit on the SQ. After you retrieve a CQE minimally, you might be interested in checking the res field of the CQE structure, which corresponds to the return value of the system call's equivalent, had you used it directly without using IO uring. For instance, a read operation under IO uring started with the IO ring op read operation issues the equivalent of the read system call. In practice, it mixes the semantics of pread and pread v2, and that it takes an explicit offset and supports using -1 for the offset to indicate that the current file position should be used instead of passing in an explicit offset. See the opcode documentation for more details. Given that IO uring is an async interface, erno is never used for passing back error information. Instead, res will contain what the equivalent system call would have returned in case of success. And in case of error, res will contain -erno. For example, if no read syscall would have returned -1 and set erno to e invalid value, then res would contain -e invalid value. If the normal system call would have returned blah blah blah. Okay. Optionally, IO uring enter can also wait for a specified number of requests to be processed by the kernel before it returns. If you specified a certain number of completions to wait for, the kernel would have placed at least those many numbers of CQEs on the CQ, which you can then readily read right after the return from IO uring enter. It is important to remember that IO requests submitted to the kernel can complete in any order. It is not necessary for the kernel to process one request after another in the order you placed them. Given that the interface is a ring, the requests are attempted in order. However, that doesn't imply any sort of ordering on their completion. When more than one request is in flight, it is possible to determine which one will complete first. When you dequeue CQEs of the CQ, you should always check with submitted request which submitted request is responsive. The most common method for doing so is utilizing the user data field in request, which is passed back on the completion side. Yes, okay. Submission queue polling. One of the goals of IO-U-ring is to provide a means for efficient I/O. To this end, IO-U-ring supports a polling mode that lets you avoid the call to IO-U-ring enter, which you use to inform the kernel that you have queued SQEs on the SQ. With SQ polling, IO-U-ring starts a kernel thread that polls the submission queue for any IO request you submit by adding SQEs. That's what we want. We want this polling mode. With SQ polling enabled, there's no need for you to call IO-U-ring enter, letting you avoid the overhead of system calls. A designated kernel thread dequeues SQEs off the SQ as you add them and dispatches them for asynchronous processing. The main steps in setting up IO-U-ring consist of mapping and the shared buffers with mmap calls. In the example program included in this man page, the function app setup U-ring sets up IO-U-ring with a queue depth deep submission queue. Pay attention to the two mmap calls that set up the shared submission and completion queues. If your kernel is older than version 5.4, 3 mmap calls are required. Okay. So this is the SQE, we looked at that. Atomic store. SQEs are added to the tail of the submission queue. The kernel picks up SQEs off the head of the SQ. To get the next available SQE and update the tail is as follows. Yes, you have some kind of mask, okay. Describer O, okay. Atomic store explicit. So an atomic store. Fences. Which memory fence is used for atomic stores? When storing Okay, so let's proceed. So Memory ordering, modern CPU, compilers and CPUs freely reorder reads and writes without affecting the program's outcome to optimize performance. Some aspects of this need to be kept in mind on SMP systems. Since IO involves buffers shared between kernel and user space, these buffers are both visible and modifiable from kernel and user space. As heads and tails belonging to these shared buffers are updated by kernel and user space, changes need to be coherently visible on either side, irrespective of whether a CPU switch took place after the kernel user mode switch happened. We use memory barriers to enforce this coherency, being significantly large subjects on their own. Memory barriers out of scope. Okay. Okay, this is the example for the acquiring of the completion queue entries. Okay, so this is the example. They set all flags to 0. I want to set something in the flags. And the params. So IO uring params. Let's look at it again. So this has, no, how does it work again? So I think we have to set flags. I think the kernel fills in some of these like features or something. Yeah. So I think what we want to set is flags. Sys flags IO uring params. So flags IO uring params flags bit set IO uring params bits U32 yank to the semicolon enum U32. Let's see. This is what we want. And let's define a macro. F this equal this down very nice macro. VI this. Okay, let's remove those things here. Good. And then, and then we said flags IO uring params, and this is IO uring params flags. Good. So back in ioring.odin, we set this equal to dot SQ poll non-fixed. Single mmap. No, this is the features. This is not the flags. I thought you'd have to set the flags. So man IO urang setup. Set up epoll, set up SQ poll. Oh, this is the setup flags. Oh, okay. And this has to be put into flags. So this is IO urang setup flags. Setup bits. And set up bits. So this is the feature, feature bits. IO urang feature. Features. Okay, so we also need IO urang setup bits. Enum U32. And take these. I think the macro should work. So record F this, give this, oh no, okay, look at this, G control A, G control A. Oh no. Okay. Okay. IO urang setup bit. So SQ poll. IO ring SQ. IO ring setup SQ poll. I think that's it. Ensure that the wake up flag is read after the tail pointer has been written. Okay, yeah. This is also something that can happen. I think there's also an this idle thing that we also have to set. SQ thread CPU, SQ thread idle. SQ thread idle. This is in milliseconds. Let's just say SQ thread idle is like 2 seconds or whatever. So params dot SQ thread idle is equal to SQ thread idle. Sys params flags. It's not params flags, it's setup flags. And features is IO uring features. Redeclaration of setup flags. What? IO uring setup bits. Why is it in here twice? Okay. That's great. So I have no idea if this works. So we call this, we get something back, probably, I mean, what do we even get back? So what's the return value of file descriptor? Yeah, it's a file descriptor, okay. Okay, this is also relevant. The rest of the fields in the struct IO uring params are filled in by the kernel and provide the information necessary to memory map the submission queue and the completion queue and the array of submission queue entries. SQ entry specifies the number of submission queue entries allocated. SQ off describes the offset of various ring buffer fields. Where's SQ off? I think it's an array. No. SQ off. Where does SQ off come from again? So that's also in the IO uring params, right? This. Yeah. So this is filled in, and we get an FD, IO FD, ring FD. If ring FD is, I mean, there are several return values here, right? Default, enval, is that also defined here? Default R6. Yeah, so probably what we want here is an enum IO uring setup error, which is backed by an int. I32. Oh no, it's the other way around, enum. And then we just take fault, and then we need to import core sys POSIX.efault. I think this is how you do it, right? So when we go back in like something like read or receive TCP. Is this how you do it? I mean, I think I remember something. An accept, maybe it was accept Linux results. Okay, I don't know. So inval POSIX dot enval file POSIX dot m file okay, let's get back here. So POSIX.enval. Okay, that's all positive. Okay. Enval. I don't even know what these things mean. Mem. I don't even know if this works. So eperm. Eperm and eperm. Whatever. Okay, if ring of D is less than 0, we just return an error. Or what do we I'm not sure. Format dot eprintln the error while setting up. Let's also say error. IO uring setup error of the ring FD. Setting up IO uring. So this is import core format. Okay. So this would be more like a IO uring setup error. And then we also have none, which is equal to 0. So error is equal to this. Return real error. Well, maybe do it like this. Good. So we have the setup call, and we would probably want to also map in all the stuff. App. It's more like man IO uring and then app setup. Okay, we want all of this here. So the S-ring size, S-ring size sq of dot array plus params dot sq entries times the size of an entry, size of unsigned, C ring size p dot cq of dot array. I mean, is this even true? Dot cq entries plus p dot cq entries. I don't even times the size of an IO ring CQE. Not P, it's P params. Params. Okay. So assert params.features IO, what was it? IO dot SQ poll IO ring feed SQ poll, I guess. And params.features this is where the arrays, I don't know. Wait, this is the string size? I don't really know why. Did they have something there? Like, man, IO ring setup, string. I thought they had something there. Oh yeah, here. Taken together, SQ entries and SQ off provide all the information necessary. The submission queue can be mapped with a call like this. GraphQL, SQ off is the okay. So now we need to memory map SQ, maybe SQ pointer, and let's see, where is mmap? We can use linux.mmap. So linux.mmap, var pointer, and erno. So this nil. The size is string size. No, it's not right. I think this is not correct. Oh yeah, it is correct. So we need one mmap call for CQ pointer is SQ pointer. IO ring of SQ ring. That's something we need as well. this is kind of weird. Okay, so this is the string size. This is map. Let's see. This is read and write. Then we want to say this prod read, prod write, map private, probably. Map share, no. Of course it has to be shared. And populate. I don't know what populate does again, so man. Populate pre-fault page share. Ah, okay, I see. It's good. Then we need the file descriptor and the offset. So this would be the ring of D and the let's env user include Linux IOU ring sq offset IO ring off. So we need these as well here. And sys. And delete all of this. This is 0 U64. U64. Good, okay. Import core sys Linux. Where's this? This is in IO ring 44. This is IO ring off, and then SQ ring. Undeclared name .io ring feed SQ poll. IO ring. IO ring feed SQ. I mean, this should be here. IO ring. Undeclared name IO ring feed SQ poll. Should be declared. Oh no, that's complete bonkers. Feed single mmap. Single mmap, right? And also let's just delete these here. Don't really need that. Okay. IO ring SQ poll, and here single mmap. Assignment count. What? What are you saying? 38. Nil. This is U and pointer, so does that work? Assignment count. Flags. So we have the address, size, prod, flags, file descriptor, and offset. Can't cast nil. Yeah, whatever, just use 0. Assignment count. Oh yeah, okay, because there's an error that can come out of this. Error now. Oh, we could have used Erno. We could have just used Erno. This course is Linux Erno, so let's drop this. Let's drop this. This is an Erno Linux. And just make it linux.erno. If Erno. So if Erno is not equal to none, I think it can only return map failed, right? Error is equal to Erno, return. Okay, next thing would be to, okay, we have a CQ pointer. I want, so S ring size. Oh. Whichever one's bigger. Okay, so if C ring size is greater than S ring size, we set the S ring size to C ring size. Is that about right? Yes. To start this here, we can also do it here. Okay, so yeah, that makes a little bit more sense. So this should encapsulate everything. CQ entry size or whatever, I don't know. So we got this. We don't need a second mmap. We say CQ and we need a second mmap. You just say 0 here, right? What? 30. String size. Are you kidding me? Can assign value string size of type u32 to uint in a procedure argument. Is this a uint? Okay, this wants to be a uint. I wonder why it did build before. Can assign value ring of d of type int to fd. Okay, let's say this is Linux. Linux.fd i32 okay, cannot assign value of type u64 to i64 in a procedure argument. Okay, now it builds. I do have to do this here? No, we don't. Okay. So next thing would be to say, okay, SQ entries is equal to mmap 0 okay, this is now the size of these SQ entries. Okay, don't really understand that, but let's see. So it's 0, then it's the size, which is params dot SQ entries times the size of an IO SQ entry, right? IO uring SQE. Then dot read. Let's actually remove these here. Dot read dot write dot shared and dot populate. The ring of D, and it also needs an offset, which is IO ring of SQEs. Yeah. And then the CQ entries. Now the CQ entries is the SQ pointer plus params dot CQ off dot CQEs. A C ring head, C ring tail. We probably only need to, I mean, we have to manipulate the tail, right? So we don't really need the head. This is, why do we need this? SQ pointer. Why don't we call this CQ pointer? Use this CQ pointer plus params dot CQ of tail, and C ring mask CQ pointer plus params dot CQ of ring mask. And we need the same thing for our SQ. So S ring head is S. Oh no, it's SQ pointer. Oh, I see. So this is. So let's say, okay, SQ CQ pointer is equal to SQ pointer. And here we say S ring head is equal to SQ pointer plus S params SQ of dot head S ring mask S ring mask SQ pointer plus params dot SQ of dot ring mask, and these entries have to be mapped separately. Okay, so let's see. Raw pointer versus U32. Yeah. So let's say okay, how do we do this? Raw pointer. Can we just add to this? Raw pointer. Is that something? Raw pointer represents a void star. Yeah, but can I do pointer arithmetic with this? So can I do something like this will also be a raw pointer, right? Or so no, this will not be a raw pointer. So SQ entries. What does mmap return? What does mmap return again? So packages mmap raw pointer. So where's the overview? Odin lang overview from raw. I mean, how do you, can you just cast this? How do you come from so these are just two raw pointers. The head should be a pointer to an SQ entry, right? No, this is no, this is an index. This is an index. Where do they write something? Submit to SQ. Yeah, it's the this is the index. Okay. So this is more. Oh, but why is it SQ pointer plus? I know it's a pointer to a U32, right? So pointer U32. And the ring mask is a also pointed to U32. And the SQ entries should be something else. It's a raw pointer right now, but this should be like IO U ring. I don't know how you cast that. It's a problem. Like this. Many pointer IO U ring SQE. Okay, so SQ pointer is a raw pointer. What if I cast this to U int pointer? U int pointer. And what if I do this? Okay, now it's UN pointer versus U32, so also this. Okay. And now we want to cast this to a pointer to U32. I don't know if that works, actually. Or if that... Okay, that's kind of unfortunate. Or do you have to say transmute like this? Okay, that would work. So maybe also here a transmute. Okay, this also Erno. SQE map Erno. SQ pointer map. SQ pointer map Erno. SQ pointer map. SQ pointer mmap. SQE mmap. If SQE mmap Erno is not equal to dot none, we set the error to SQE mmap Erno and return. Okay, so we cannot transmute. Oh yeah, that doesn't make sense. So SQ entries is now SQ entries raw, and SQ entries, which is a many pointer to an IO U ring SQE transmute. Now I wonder how I get IO U ring SQE. Now I wonder how I get this to be sized. Uint countersign value. Okay, also this has to be an I64. Okay, same thing here. So we have to transmute this to a U32 pointer, because this is just an index. This is a U32, and no, this is also U32 pointer, and this is something else. Pointer to U32. Transmute pointer to U32. Okay, so this is maybe like raw uint pointer. Transmute to a many pointer IO uring CQE. Okay, so this builds, but obviously I want this to be sized, but I don't really know how I do that. Odin, how do I convert a many pointer to a slice? Is it just by IO uring CQE CQ entries? Okay, so how do I make this a slice? By params.cq entries. CQ okay, so this is how I do that. So SQ entries, we have to transmute this as that, and then get params.sq entries to make this a slice of IO uring SQE. Okay, that works. Okay, so we have that set up. We want to return something. So let's say our IO uring setup. This is kind of a struct. And this has maybe a ring fd, which is a linux.fd. It has an S ring head, which is pointer U32, S ring mask. Now we probably also need the tail, right? So when we write, or when we read, Yeah, we also need the tail for this. Oh no, wait a second. CQE head. SMP load acquire what? Do we need also here head and tail? I think we only need to update the tail. Is that right? I believe so. S-ring, S-ring, tail. So we got the S-ring head here. Okay. S-ring mask, we need the C-ring head, C-ring tail, U32, C-ring head, U32, C-ring mask, pointer to U32, although that shouldn't change. C-ring mask. Yeah, it's also pointer. Don't know why you would want this to be a pointer. I mean, does it change? I don't know. So CQ entries is this, and then, oh man, params dot CQ entries. Okay, so we have SQ entries, which is IO uring SQE, and CQ entries IO uring CQE. I think that's it. So this is kind of the result, which is a IO uring setup, or IO ring. Okay. Say result dot ring fd is equal to this. Yeah, no. Okay, then this is result dot. Don't need this here. This is result dot. Result dot. This would be better if it's here. Result dot and result dot. Okay, then here result dot. See if that's enough. C-ring tail, yep, that's not necessary. And this one, okay. IO ring setup. Okay, let's go then back to Linux, IOU ring, setup. Okay, this is great. And this returns an IO ring, a ring, and error. Erno if erno is not equal to dot none. Eprint line and return cannot set, unable to set up IO ring. Okay, be right back. So there's something like need wake up. Need wake up. Okay, this is part of the S-ring flags. Okay. I think this was an nvim IO ring setup. No, man IO ring setup. Need wake up, yes. Oh, forgot my water. I think what we want to do, let's make it to do here. Implement adding to the S submission queue and reading from the completion queue. Keep in mind to check the SQ ring flags. So where was the SQ ring? That was part of the params, right? SQ ring? No. Where did the SQ ring come from? Off IO SQ. Where did that come from? Flags. Okay. Is there also flags for this? User adder. Yeah, so that's something that was not in there, right? IO ring. So let's also say SQ ring flags. pointer u32 and CQ ring flags. I don't know if we need them, but so S ring flags and C ring flags, and result.S ring flags equal transmute u32 u int pointer sq pointer plus u int pointer params sq of dot flags. Same thing for this, but it's for the C ring, CQ pointer, CQ, okay, C ring flags. Okay. These flags have to be checked for need wake up. Let's actually copy them and sys put them in here and say this is IO U ring or IO ring or more like S ring flags, S ring bits, IO ring SQ. Okay, maybe we call this IO ring SQ bits. IO ring SQ flags bit set IO ring SQ bits, and do we have that also for the CQ flags? IO ring CQ flag CQ ring flags. There's only one, so that's kind of, so maybe we don't even have that. Okay, so that builds, I guess, yeah, maybe we can try and run this in LLDB, and let's see where we get. So break at IO U ring I mean, which file is it? So it's IO U ring slash U ring IO ring dot odin, and then it's line 25. Run. Print the params. Okay. Print params. SQ poll is true, and thread idle okay. So let's see what happens. Result dot ring FD. Okay, it seems to work. So print the params. Oh yeah, it filled it in. It filled it in, right? So features, single mmap, true. All these things true, great. And the offsets, head and tail, ring mask. This is where the tail lives, this is where the head lives. Now we have to map this into user space. Print the S ring size, print the C ring size. Okay. Now print SQ pointer. Okay, that's something. So we successfully mapped that into our user space, this SQ pointer business, which is basically where the CQ entries live, where all of these offsets live. No, not where the offsets live, where the head, tail, and mask live. And then we also have to map in the SQ entries. Wrong. It's also something. Okay, I would not have suspected that this works. So 64 SQ entries and 128 CQ entries. Whoa. Would not have thought this. Okay, this works. So let's say git status, git add all, git commit. So added IO uring layer and also setup functionality. Git push origin mass main. Okay, this was successful. We set up our IO ring and can use it for reading and writing from now on. But I will do a break and I will eat something. Yeah, I don't think I will come back online today again. So have a nice day.